Hey you, what's good? This is a push swap tutorial. It's a 42 project that sorts a stack in C. A few things before we get into it. It's my first time creating a video for YouTube and I'm kind of newish to coding, so I'm definitely not an expert in either of these things. I thought I'd do this video as a way to help me practice, defend and explain problem solving processes, because problem solving is one thing but being able to explain it is another. So yeah, thanks for tuning in. The objectives of the project is we have at our disposal two stacks named A and B, and we will be creating a program and implementing a sorting algorithm inside our program. Our program will take as parameters a random set of numbers, negative or positive, and without duplicates. It needs to be able to handle both types of inputs, so either as a variable number of command line arguments or as a string, so the numbers between the quotation marks like you see here and separated by a space. Next, we implement an algorithm that sorts in ascending order the input of these numbers. Our algorithm will consist of swap, rotate, reverse rotate, and push operations, and we will talk more about these later. After taking in an input of numbers and passing them through our algorithm, our program should output the list of operations that it's done. To pass the evaluation, our program will need to return us a certain amount of instructions for sorting X number of values. So for example, if our input of random numbers had 3 numbers, then the program will need to return us a list of operations that is less than or equal to 3. And for an input of 5 random numbers, then the list of operations will need to be less than or equal to 12. And you can see the guide here for an input of 100 numbers and for 500 numbers. Now, the lesser the instructions our program returns to us, the more evaluation points that we will get. In this tutorial, together we will be creating the stacks, looking at the swap, rotate, reverse rotate, and push operations, choosing a sort algorithm, writing pseudocode, and then coding the algorithm. And then in the end, we will be testing our program with a checker that's provided by 42. So what is a stack? You can think of it as a stack of boxes piled on top of each other. It's going to have a top box and a bottom box. At this point, I'd like to give a shout out to Oceano. He's also made a video on this project. I'll leave a link in the description below. But thanks to his video, I've learnt a lot about stacks and linked lists that has helped me a great deal on getting this project started. You'll find that much of my work were made possible from learning from him, so please do check him out. Alright, back to our stacks. So we will be creating our stacks with linked lists, and if you completed the libft bonus, you'd be familiar with this concept also. A linked list is an organized data structure that contains nodes. These nodes are data elements. So referring to our picture earlier of a stack of boxes, consider each node like a box, and it stores data inside of it, for example, a number, as we have seen. What makes this data structure a linked list is that each node is connected in sequence, kind of like a chain. So in sequence means the head node is connected to the next node, which is connected to the next, and so on, and which is connected to the tail node. We will interchangeably be using top with head and bottom with tail. What we're looking at here is a singly linked list. So the chain from top to bottom is unidirectional. For this project though, we will be using a doubly linked list, which means the nodes are linked bidirectionally. So each node has a reference to a next node, as we have seen so far, and it also has a reference to a previous node. The tail's next reference always points to null to signify the end of a linked list, unless it's a circular linked list though. A circular linked list can be either unidirectional or bidirectional, but the tail node in a circular linked list is linked to the head node, and we will not be using this. Recall, a node is like a box containing data, and it can contain many different types of data you want. For our project though, our nodes will contain two main things. The data, which will consist of a number and its position or index in the stack. There are a few more data things, but we will get back to this later. Our nodes will also have reference pointers, a pointer to the next node and a pointer to the previous node. There will be a third pointer, but we will get back to this when it will make more sense. Now that we have our stack, let's look at what each operation does. Swap A swaps the first two nodes in A. Swap B swaps the first two nodes in B. And SS means we will be simultaneously swapping both the first two nodes of A and B at the same time. Rotate A brings the top A node to the bottom and shifting the remaining nodes upwards. Rotate B does the same thing. And RR means we're rotating both A and B at the same time. Reverse rotate A, so instead of bringing the top node to the bottom, we're bringing the bottom node to the top of the stack and shifting the rest of the nodes downwards. Reverse rotate B, the same thing. And then RRR means I sounded like a pirate then. It means we are simultaneously reverse rotating stacks A and B at the same time. Push A means we are pushing the top node of B on top of stack A, and push B means we are pushing the top node of A on top of stack B. I've looked at several different algorithms and in the end chose what felt the simplest and most intuitive. It's called the Turk algorithm, coined by Ali Yeat. I hope I said your name right. You can look at why he called it that in his article here. Shout out to Ali. This Turk algorithm returned me the least amount of instructions on average and passed my project with 100%. What this algorithm does is it pushes the nodes from stack A to stack B until there are only 3 left in stack A. However, each time an A node is pushed to stack B, it sorts the nodes in stack B at the same time and in descending order. Let's take a closer look at what happens step by step. We have a stack with more than 3 nodes. We push the first 2 nodes from stack A without checking anything. We now have in stack B a biggest number so far and a smallest number so far. This is important to push the rest of our A nodes. Just a side note, let's say for example we had a stack of 4 nodes. We would then only push the first A node to stack B, because after this our 3 left in stack A condition is met. After pushing the first 2 A nodes to stack B, we now look for target nodes. From here, every A node needs a target node in stack B. A target node has a smaller value than A, but the closest smaller value to A. This will make a lot more sense a bit later. Recall, each time we push A node to stack B, we are sorting stack B at the same time in descending order. So that's why each time we push A on top of a B node, we need to make sure that A has a larger value than B. Let's take a look at our top A node here, which is number 25. Its target node from B will be 0, because that is the only value that is smaller than 25. Now, if A node can't find a target node that contains a closest smaller value, its target node will then be the node with the max value, so the largest number. And you will soon see why this logic makes sense if you haven't pictured it already. For example, minus 38 here. In B, there is no number that is smaller than minus 38, so its target node will be the max value, which is 99 in this case. Our target node for number 10 will be 0. Our target node for 7 is 0. And our target node for 42 is also 0. In this configuration of the program, every A node is now assigned its target node. The next step, and after each configuration from here on until we have only 3 nodes left in stack A, we need to calculate which A node we should push to stack B. In other words, from this point on and after each push, we need to find which A node is the cheapest to push to stack B. The formula to find the cheapest node to push is the sum of how many operations will it take to bring A on top, and how many operations will it take to bring A's target node on top, and that gives us our push cost. Let's calculate together the push cost for every A node, do the instructions needed, then finally push the cheapest node. Our push cost for 25 is 0 because it's already on the top, and its target node, which is 0, is also already on the top. Since the cost of 25 is 0, we won't need to calculate the rest of the node's push cost. The way this analysis works is, once we have the first node's push cost, which in this case is 0, we need to find something cheaper. But since you can't get any cheaper than 0, and even if there's another node whose push cost is 0, we will go with the first one by default. After pushing 25 to stack B, we now need to calculate again for each A node its target node, then the cheapest A node to push. Recall, as long as our stack A has more than 3 nodes, we will keep doing this until there are only 3 left in A. The target node for minus 38 is 99. For number 10, its target node is 0. For number 7, its target node is also 0. For 42, its target node is 25. You can see in this example that In stack B, 0 is also smaller than 42, but 25 is the closest smaller to 42, so it's the number that is closest to 42. Now, the push cost for minus 38 is 1. Why? Because its target node is 99 and it only takes one operation to bring 99 to the top of the stack, and which is reverse rotate B. The push cost for 10 is only 1 because we can simultaneously rotate A and B at the same time to bring 10 and 0 to the top of the stacks. The push cost for 7 is 3, and the push cost for 42 is 1 because we only need to reverse rotate A to take 42 to the top. As you can see, we haven't found a push cost that is cheaper than minus 38, so we'll go ahead and do the operations and push minus 38. We now have 3 nodes left in stack A, and in this case, we will implement an algorithm that sorts a stack of 3 nodes in ascending order. And it's pretty simple. We just need to make sure that the biggest number is on the bottom, and if we need to, we just simply swap the first 2 nodes. Now we will push every B node one by one from the top of the stack until B is empty. The only requirement for this step is that before we push B node to stack A, we need to make sure it will be pushed on top of the correct A node. Recall, our program needs to sort stack A in ascending order. So this means that for every B node, it needs a target node in stack A that has the closest bigger value to B node. If B node can't find its closest bigger value, let's say because it already is the largest number, then yep, you guessed it, its target node will be the smallest number in stack A. I'm sorry, I've got some birds singing in the background because for some reason they're very happy. Let's have a look at the first B node and set its target node. And the closest bigger to minus 38 is number 7. So 7 is its target node. We are lucky that 7 is already on top, so we simply just need to push. The target node for 99 is minus 38 because there is no number bigger than 99, so its target node will be the smallest number. Again, we are lucky that minus 38 is already on top. The target node for number 25 is 42 because even though 99 is bigger than 25, 42 is the closest number to 25. Now we either rotate or reverse rotate stack A so that the target node is on top. Imagine a line right in the middle of stack A. This helps us figure out whether we rotate or reverse rotate depending on whether the target node is above or below this line. If our target node is above the line, then it will take less instructions if we do rotate. And if our target node is below the line, it will take less instructions to do reverse rotate to bring our target node to the top. In this current state, we reverse rotate to bring our target node to the top. Our target node for 0 is number 7. And 7 is below the median line, so we reverse rotate until 7 is at the top. Finally, we move the nodes in stack A to ensure that the smallest number is on top and the biggest number is on the bottom of the stack. Then we look at where the smallest number is in the stack. It will either be above the median line or below the median line, and so then we rotate or reverse rotate accordingly. There we have it, the Turk algorithm. To summarize, if a stack has more than 3 nodes, we push A node to stack B twice, and until 3 is left in stack A, we push the rest of A nodes to B, simultaneously sorting stack B in descending order. We then use our sort 3 algorithm and then push all the B nodes back into stack A and making sure that A is in the right position before each push. And finally, we move the smallest number on top of the stack. In the next part of the video, we will write our pseudocode, code our algorithm, and then test our algorithm. We start by declaring pointers to 2 data structures, one for stack A and another for stack B, and we set them to null. We then handle input count errors. Our argument count has to be 2 or more, and it can't be empty. Then we handle both cases of input, so whether it's a variable number of command line arguments or it's a string. If it is a string, then we need to split the string into substrings. In other words, we will be extracting every individual number inside the string. We then need to initialize our stack by taking all of the individual numbers and putting them inside a stack. And we need to make sure that each node is a number or a negative or positive sign. If the input of numbers is in fact a string, we need to convert each individual number to a long integer. The reason why we use a long integer and not just an integer is so that we can handle larger numbers. Now, if the input meets all of our conditions and there are no errors, then we append each number inside a node to the stack. Once we have our stack ready, we check if it's sorted, and if it's not sorted, then we implement our sorting algorithm. There are some basic functions we will need, though I won't be going through them in this video, but feel free to have a look at them on my GitHub. So we will need functions to handle input errors and free the stacks when needed. We need functions that do the swap, rotate, reverse, rotate, and push operations. We will also need functions that finds the length of a stack, finds the last node, finds the smallest number, and then finds the biggest number. At this point, we have a basic understanding of what stacks are and that they can be created with linked lists. We know what the swap, rotate, reverse rotate, and push operations are. We know how the algorithm works, and we know what functions we roughly need thanks to our pseudocode. In our header file, we will be including the standard Boolean library. You will see that the Boolean flags will be used for the purpose of printing the list of our commands. We also include the limits library, which has the integer, min, and max macros defined. I've incorporated my libft and function printf functions to use in this project, but just make sure that you include any necessary headers here. In our header file, we will define our data structure and call it sStackNode. This will be our box for each node. Recall earlier we said that each box, which is a node, contains the data, which consists of a value and its index. We also said that there would be a few more, which you will recall. They are things that we already talked about, and they are push costs, above median, and cheapest. Recall also earlier we said each node contains reference pointers to the next node and to the previous node. We also said that there would be a third reference pointer. This will be the target node, a term we've also already talked about. So that is our struct defined. And finally, we will name this new struct we created tStackNode, which we can call in our functions from here on out. The way this works is, so earlier we called our struct sStackNode, and this is like the official name of our struct. Now that we have it defined, we can give it a new name, tStackNode, and this is like the shortened name for our type, so we don't have to call struct sStackNode each time we want to use this newly created struct type. Now in the rest of your header file, just make sure that you include all of the functions that aren't static. Let's have a look at our main program. We declare pointers to two stacks and set them to null. We check if the argument count is correct, so it would need to be 2 or more. The first argument would be the executable name, and the second argument should be a number. If the argument count is only 2, then it is likely that our second argument is a string of numbers, and so then we will need to call our split function to extract those numbers. We then initialize stack A with the input of numbers. We see argv plus 1 here is because we want to start from the second element of the command arguments, because the first element is the program name. Then we check if our stack is sorted. If it isn't, then we pass it through our algorithm. And finally, we clean up our stack. This is our split function, which is a little bit different than the one that we did for libft. My birds are being happy again. Similarly to our function split in libft, we've got a function that counts the words. We have a function that copies the substring, and we have our main split function. The difference in this split function is we use a static integer variable called cursor, and it acts like a cursor that moves along each character of the string. What this does is each time the getNextWord function is called, it is able to pick up where it last left off in the string. Then it can continue to extract the next substring. Similarly to how a getNextLine works. For our stack initialization function, we declare a long integer to store our value, and we have a variable that will be used to iterate through our array of numbers. The code is pretty self-explanatory. We check for any syntax errors, and then if the argument is a string, then we use function a2long to convert the string to a long integer. Then we check for integer overflow, and if there are no errors, then we finally append our node that contains the value n. To append our nodes, we will need a pointer variable for our new node, and we need a pointer variable to the last node for our new node to be appended from. And we check if the stack is empty before we allocate memory for the new node. We check if memory allocation is successful, and then we set the new node's next pointer to null, since it's going to be the last node in the list. Then we set the number as the value for our new node. In the next part of the code, we need to check if the stack is initially empty, because if it is, then our new node will be the first and only node so far. If it is empty, then we update the top pointer of the stack to point to our new node, effectively making it the new head of a linked list. And since it is the first and only node, we will need to set the previous pointer to null. If the stack isn't empty, then it means that there are already existing nodes in our list, in which case we need to find which node is the last one, and then we append our new node to that last node. We then complete the appending by updating the previous pointer of our new node, which needs to be pointing to our old last node. We're now up to our stack sorted function, which is a boolean, which means that it will either return true or false. As per good practice, it checks if the stack is empty. As it iterates through the stack, then as it iterates through the nodes in the stack, it will keep checking whether the node after the previous has a greater value. Because our stack needs to be sorted in ascending, this will mean that our stack is not sorted. If our stack isn't sorted and it only has 2 nodes, then recall we do a simple swap. If the stack has 3 nodes, then we will implement our simple sort3 algorithm. Otherwise, if it has more than 3 nodes, then we will implement our Turk algorithm. Our sort3 function, pretty simple. We need a pointer variable to point to the biggest number, and we simply check if the biggest number is at the top, and if so, we just rotate it to the bottom. If our second node is the biggest node, then we just reverse rotate the stack, shifting our biggest node to the bottom. Now that our biggest number is on the bottom, we just check if the top number is larger than the second. If so, we just swap. We're now up to our big sort stacks function, which will take some patience to get through. We've got a variable to store the length of our stack. Then we go ahead and check if our stack has more than 3 nodes. If so, we just go ahead and push B. After that, if our stack still has more than 3 nodes, then we push B again. after which we check again if there are still more than 3 nodes in A, in which case we prepare the rest of our A nodes so we can push them to stack B. We've got init nodes A here, which calls the relevant functions in order to prepare our nodes in A for us. So at each configuration, it sets and refreshes the current positions of the nodes. It sets the target, it calculates the push cost, and it also sets whether or not that A node is the cheapest. Our current index function here, it does 2 things. One, it sets the index or position of the current node, and 2, it sets our Boolean above median data to true or false depending on where it is on the line. And the median line is simply just the length of the stack divided by 2. Here we iterate through the stack, and for the current node we set its index, and then we check whether the index is above the median or below the median, and we set the Boolean flag. Then we move to the next node in the stack for processing. This is the function that sets for A its target node from B. We need a variable pointer that points to the current B node. This target node pointer is a data element that is inside of our data structure, and we will need it to point to its target node. We've got a long variable to store our best match index. In other words, this is what keeps track of the closest smaller number so far. And by default, we assign to it the smallest long integer. We will now go through every B node in stack B to look for a target node for A. For the current B node, we check if it's smaller than A, but also bigger than the closest smaller so far. If it is, then we update the best match index to the number that we found in B, and we update the target node pointer to point to the current B node. This means that for the current A node, we have found its target. We then move to the next B node for comparison and see if we can find a closer, smaller number, so even a better match. After going through all of our nodes in B, we check if the best match index hasn't changed from the default value that we've assigned to it earlier. If this is the case, then it means that we haven't found a number smaller than A, in which case we set A's target node to the biggest number in stack B. Otherwise, we set A's target node to wherever the target node pointer pointed to during our while loop earlier. Then we move to the next A node to look for its target node. We've then got our cost analysis function that calculates the push cost for each A node, which is the sum of the amount of rotations it will take for A to be on top, plus the amount of rotations it takes for the target node to be on top. This is where we use basic mathematics, taking advantage of the indices and the median line. We've got our set cheapest function here, and what it does is it uses the push cost data that we had just calculated before for each node, and it goes through all of the nodes and it searches for the cheapest value. so whichever node has the lowest push cost, and it would set for that node the Boolean cheapest to true. After initializing and preparing all of our nodes in A and setting its target nodes, we're now ready for pushing them to B. We have our move A to B function, which is fairly simple. We've got a pointer variable that will point to us the cheapest node in the stack. And the get cheapest function is fairly basic. All it is it looks through all of the nodes in the stack and finds the node where it has its Boolean cheapest set to true. We then check if both the cheapest node and the target node is above the median. If so, we just do one operation, which is rotate both. You can see in our rotate both function, we've accounted for if either the cheapest node or the target node is on top of the stack, because in that case, we don't want to rotate it. So in our rotate both function here, we make sure that the current top nodes are not the cheapest node and not the target node. Then we will do the operation. Then we refresh the current positions of all the nodes after the operation. Now this false parameter here is a Boolean value, and when it's set to false, it means that we are wanting to print the operation to the output. So just like before, we checked if both the cheapest node and its target is above the median. This time we're checking if it's below the median, and in which case we reverse rotate both. We then do a final preparation to make sure that both our cheapest node and target nodes are on top of the stack, and we have a function prep for push that does the rotate or reverse rotate operations until the node we want is on top. And then we finally push to stack B our A node. By now we should only have 3 nodes left in A, and we go ahead and sort that. Now we push all the B nodes back into A. Initializing and preparing the nodes in B only involves setting the current indices and setting the target node for B. The function for setting the target node for B is just like the one that we did for A. But instead of looking for the closest smaller number, this time we're looking for the closest bigger number. To do this, we assign to our best match index the biggest long integer by default, and then we go through all of the nodes in A to check for the target node for B. We check if the current number in A is bigger than B, but also smaller than the closest bigger number so far. If we found a match, then we update the best match index to the value in that current A node, and then we set the target node pointer to point to that current A node. And then we move to the A node to see if we can find an even better match. If after going through all the nodes in A and the best match index hasn't changed from the default value that we've assigned to it earlier, this means that B couldn't find anything bigger, so then its target node will be whatever the smallest number is in A. Otherwise, we set our B's target node to the match that it has found earlier in our while loop before going to the next B node and finding its target. Now we do a final preparation before pushing our B node back to A. We just want to make sure that our target node is on top of the stack, and then we push. After each push, we refresh the current positions of all of the nodes, and finally complete the sorting by making sure that the smallest number is on top of the stack. For this, we just enter into a while loop, so as long as the smallest number is not the top of the stack, if it's above the median line, we do a rotate, otherwise we reverse rotate. Once again, these are the amount of instructions or operations that our push swap will need to return for us to pass our evaluation. So now we will test our program against the checker that has been provided by 42, and let's see how 3 numbers will do. So OK just means that it has sorted without any errors. The WC-L is a command that just returns us how many lines it has read. So it gives us an indication of how many instructions that our program has done to sort our stack. Now we're testing with 5 random numbers. And now we're going to test with 100 random numbers. Just make sure that when you generate random numbers online and you copy and paste it into your terminal, make sure that there are no spaces between the quotation marks. Now we will test with 500 random numbers. Let's check how many instructions it's done. So you can see 5,311, which is a pretty good number. And that brings us to the end of the video. Thank you so much for checking it out. Just recording off of my phone, so the sound is probably terrible. I also talk quite slow, so hopefully I haven't put you to sleep. I do hope that this video has been helpful somehow. But yeah, thanks again and good luck with your project. Ciao!